Hello children, welcome to online classes. Today we are going to discuss one of the most important topics in first year chemistry, that is chemical and ionic equilibrium. Let us start with the definition, meaning of rate of reaction. Rate of reaction is change in the molar concentration of one of the reactants or products per unit time. So change in the concentration of one of the products or reactants per unit time is called rate of reaction. It is represented as plus or minus dC by dt. Plus or minus dC by dt. The concentration increases with respect to products and the concentration decreases with respect to reactants, and therefore we are using plus or minus. So the concentration is decreasing with respect to reactants and the concentration is increasing with respect to products, and therefore we are using plus or minus sign. For a reaction A plus 2B giving rise to 3C plus 4D, the rate of reaction is given as rate is equal to minus dA by dt minus dA by dt is also equal to 1 by 2 of dB by dt, also equal to 1/3 of dC by dt, also equal to 1/4 of dB by dt we have. Here with respect to reactants, negative sign is assigned. With respect to reactants A and then B, we are assigning a negative sign here, and with respect to products, a positive sign is given, the plus and then plus sign here now. So rate with respect to reactants is given with respect to reactant assigned a negative sign. With respect to products, it is assigned a positive sign here. Now the factors influencing the rate of reaction. Factors influencing the rate of reaction. It depends upon the nature of reactants. So nature of reactants, in general, ionic reactions are fast and instantaneous, while covalent reactions are slow. Depends upon the temperature. The rate of reaction will be increasing with the increase in the temperature. We'll see details afterwards. The concentration of reactants, the rate of reaction increases with the increase in concentration except that of zero order reactions. A catalyst, always we are using a positive catalyst here. Positive catalyst increases the rate of reaction, means adding a catalyst, always the rate of reaction will be increased. Let us take one by one nature of reactants now. Nature of reactants means we need to see the nature of bond that is present between the reactant molecules now. So for example, when you take aqueous solutions of ionic compounds, they contain free ions in them. So during their reaction, just rearrangement of ions takes place. Hence reactions are very fast in the case of ionic reactions. Let us take an example. If we take AgNO3, say you are using aqueous solution here. AgNO3 aqueous solution, combining with NaCl ionic compound, using again your aqueous solution, it forms a precipitation of AgCl plus byproduct is NaNO3, again aqueous solution we have. So as soon as you mix these two components, immediately we are going to get a precipitation of AgCl, means the reaction is very fast. Reaction is very fast in the case of the ionic compounds. Now, in the case of covalent molecules, during the reaction, bonds have to break and new bonds have to form. This takes place some time. Therefore, covalent reactions are slow. So, during the reaction, the bonds are breaking and bonds are forming. In the case of covalent reactions, therefore, the reaction is slow. So, for example, when you take reaction between, say, H2 and then Br2, giving rise to HBr, the reaction is slow because at the time of reaction, H2 breaks down into H, 2 hydrogen atoms, and Br2 breaks down into 2 bromine atoms. Then the 2 atoms have to combine to form HBr. This takes certain time, and therefore reactions are slow. So in general, covalent reactions are slow and ionic reactions are fast. When it comes to temperature here, to know the effect of temperature, effect of temperature on the rate of reaction, energetics of reaction must be properly understood. Energetics of reaction must be properly understood. That is, reaction can be considered as two parts: bond breaking, that is endothermic in nature, and bond forming, that is exothermic in nature. Therefore, when temperature is increased, energy increases, and hence breaking of bonds becomes very much easier now. Hence, the reaction will be very fast. So, when you are increasing the energy, the reactant bonds will break very much easily, and hence the formation of the products also becomes easily, and therefore rate of reaction will be increasing. So, higher the temperature, you can say higher the rate of reaction. Then, law of mass action. It states that at a constant temperature, the rate of a chemical reaction is directly proportional to the product of active masses of reactants. It states that at a constant temperature, the rate of chemical reaction is directly proportional to product of active masses of reacting substances. Now, when you use the word active mass, so active mass is molar concentration in the case of aqueous solutions and expressed in moles per liter, or partial pressures in the case of gaseous components and expressed in terms of Newton per meter square, or you can take even in terms of atmospheres. So active mass means molar concentrations. If you take aqueous solutions, it will be partial pressure if you take the gaseous components. That is the meaning of active mass. Now, for a reaction 2A plus 3B giving rise to C plus D, the rate of reaction is given as, according to law of mass action, rate can be given as K into A square plus B cube you have. Means these two are the coefficients here, where K is the rate constant or a specific rate of a reaction. Now here, specific rate can be defined as, so let us take rate is given as rate constant into it is A square into B cube you have. Suppose if you take A is equal to B is equal to 1, then rate becomes equal to K itself now. So therefore, rate constant K is defined as rate of reaction when the concentrations of reactants are taken as unity. Means when you take concentration of A is equal to B and that is equal to unity, then the rate becomes equal to rate constant. Therefore, rate constant can be defined as rate of reaction when the concentration of reactants is taken as unity. And units of K depends upon the nature of reaction. Units of K depends on the nature of reaction. The rate equation gives the relation between the rate of reaction and the molar concentration of reacting substances. Rate equation, or you can call it as rate law, that gives the relation between the rate of reaction and the molar concentration of reacting substances. Means, for example, when you take a reaction like A plus B giving rise to some products P here now. So, rate is equal to rate constant K into concentration of A into concentration of B. This relation is called rate equation, also called rate law, which gives the relation between the rate of reaction and the concentration of reacting substances now. Reacting substances. The rate of reaction decreases continuously with respect to time. The rate is depending upon the concentrations, and the concentration in turn, these two depend upon the time, because concentration of reactants decrease continuously with respect to time, and thereby rate of reaction also decreases. So rate is depending upon concentration and concentration depending upon the time. So as time runs, concentration of reactants are decreasing, and thereby rate of reaction also decreases with respect to time. So rate is not a constant, rate always decreases with respect to time. Then comes the chemical equilibrium. For this we want to know meaning of a reversible reaction first. A reaction which proceeds in both the directions is called a reversible reaction. Both the directions means here reactants have to convert into products, and then products must convert into reactants also. Reactants have to convert into products, and products must convert into reactants. Such type of reaction can be called as a reversible reaction. And coming towards chemical equilibrium. Chemical equilibrium is a state of a reversible reaction at which the rate of forward reaction becomes equal to rate of backward reaction at a constant temperature. So chemical equilibrium can be defined as a state of a reversible reaction at which rate of forward reaction becomes equal to rate of backward reaction at a constant temperature. That can be called as chemical equilibrium. Then comes type of equilibria. We have different types of equilibrium. The first one is called physical equilibrium. In physical equilibria, the equilibrium exists between the physical states of the components, that is, in which the opposing processes involve the physical changes only. They involve only the physical changes there now. So for example, solid to liquid we have means something like ice to water. Here the rate of melting of ice must be equal to rate of freezing of water. When both the rates are equal, we can say it's a physical equilibrium between the solid and the liquid we have. Then comes gas to liquid we have. Water and steam we can take. Here the rate of evaporation of water must be equal to rate of condensation of steam. Then we can say both of them are in equilibrium. That is also said to be in physical equilibrium because only we can see the change in the physical state, that is a liquid is changing into gaseous state. Again gas also becomes there to liquid state now. When it comes to the case of solubility, so solubility, that is solids dissolving in say liquids now. So sugar dissolved in say water. So when you take here a beaker containing water, beaker having water in this, and when you dissolve say sugar, preparing a saturated solution here, we can see some solute particles also present here now. Now in this case, sugar dissolved in water here. So the rate of dissolution of sugar, how much amount of sugar dissolves per unit time, if it is equal to rate of precipitation of sugar, means precipitation of sugar here, then we can say it is nothing but physical equilibrium also now. So it can be, physical equilibrium can be between dissolved solute and solute in the solution there now. Dissolved solute will be in solution, undissolved will be in the form of precipitation. There is precipitation there now. Between these two also we have an equilibrium existing. It is also called physical equilibrium. Then coming towards another dissolution we have, that's to say gas and solution there now. Now here rate of dissolution of oxygen gas should be equal to rate of liberation of oxygen gas from the solution or from the liquid. That can be also taken as physical equilibrium. Rate of dissolution of oxygen gas should be equal to rate of liberation of oxygen gas from solution. It is also in a physical equilibrium. And finally in the case of sublimation, so for example, when you take say iodine solid here, becoming iodine, say gaseous state here now. In the case of solids which is sublime, here the rate of sublimation of iodine must be equal to rate of formation of iodine from gaseous iodine. So here the rate of sublimation of iodine must be equal to rate of formation of iodine from the gaseous state. That can be taken as physical equilibria. Then comes meaning of triple point. The temperature and pressure at which all three physical states of a substance can exist together in equilibrium. The temperature and the pressure at which all three physical states should be at equilibrium. That is said to be a triple point. Now when you take water, ice and water vapor, three exist at 0.0098 degrees Celsius and 4.58 atmosphere pressure. So this temperature and pressure itself is called triple point. So temperature and pressure at which all three physical states exist in equilibrium is called a triple point. Then comes chemical equilibrium. So till now we have seen physical equilibria. Now comes the chemical equilibrium. So chemical equilibrium is a state in a reversible reaction at which rate of forward reaction becomes equal to rate of backward reaction. So rate of forward must become equal to rate of backward reaction. At that state itself is called chemical equilibrium. In chemical equilibrium, in the equilibrium state, the concentration of reactants and products do not change with respect to time. So as time runs, the concentration of reactants and products do not change, they always remain constant. Chemical equilibrium is also dynamic in nature. It's a dynamic in nature, as well as the concentration of reactants and products do not change with respect to time. And then comes, now it can be attained from either direction. Can be attained from either direction means, so for example, when you take we can attain equilibrium between H2, I2 and HI, say by starting with H2 and then I2. Or even we can attain equilibrium by starting with HI to H2 and I2. So in either direction we can attain the equilibrium, means we can attain equilibrium from the reactants or even from the products also we can attain equilibrium state now. Attainment of equilibrium is independent of the catalyst now. Whether we use a catalyst or we do not use a catalyst, we can attain equilibrium. But only thing is we are using catalyst, we can attain equilibrium fastly. There is only the presence of catalyst. Otherwise, we can attain equilibrium even without using catalyst also. If one or else all of the components of equilibrium is a gaseous state, then it is attained only in the closed vessel. So one or else all of them it can be. Suppose take a reaction between calcium carbonate, say in equilibrium with calcium oxide plus carbon dioxide here. When you take this equilibrium reaction, say in open vessel, the carbon dioxide gas escapes and thereby backward reaction cannot take place because one of the products is not there. In such a case, we cannot attain equilibrium because one of the components is escaping into atmosphere. So, if one of the components or more components of an equilibrium system or say gaseous state, we cannot attain equilibrium in open vessel. We can attain equilibrium only in the closed vessels because one of the components escapes off. And finally, at equilibrium, delta G value remains 0. At equilibrium, delta G value remains 0. These are the important properties of equilibrium. Then comes equilibrium constant. Let us take a reaction like AA plus BB giving rise to CC plus DD. In this case, let us take rate of forward reaction. Say rate of forward reaction is equal to, so forward reaction rate constant into concentration of A to the power of A into concentration of B power B. This can be obtained from law of mass action. Similarly, rate of backward reaction is equal to backward reaction rate constant into C to the power of C we have and concentration of D to the power of D we have. Now when you take at equilibrium, both the rates will be equal at equilibrium state. So at equilibrium, both forward and backward rates are equal. So equating, so Kf into concentration of A to the power of A into concentration of B to the power of B, which is equal to Kb backward reaction rate constant into concentration of C to the power of C into that of D to the power of D we have. Now when you divide say Kf by Kb, both are constants. We are going to get some other constant. Let us take it as say Kc, which is called equilibrium constant, which becomes equal to C to the power of C here and then D to the power of D we have by concentration of A to the power of A and that of B to the power of B we have. So this can be called as equilibrium constant Kc. So it can be defined as a ratio of forward reaction rate constant to backward reaction rate constant. That can be defined as equilibrium constant. So equilibrium constant in terms of concentrations will be C power C into D power D by A power A into B power B. We have now ratio of forward reaction rate constant to, that is, it is defined as ratio of rate constants of the forward reaction rate constant to backward reaction rate constant, that is Kf by Kb itself is called equilibrium constant. Suppose if you have a gaseous equilibrium, gaseous state, then the equilibrium constant is expressed in terms of partial pressures. In terms of the partial pressures, where the terms concentration are replaced by partial pressures. So it is partial pressure of C to the power of C, pressure of D power D by partial pressure of A to the power of A and pressure of B to the power of B we have. And the Kp and Kc related as Kp is equal to Kc into RT to the power of delta N. This delta N G gives rise to number of moles of gaseous products, minus number of moles of gaseous reactants we have. So difference between the number of moles of gaseous products and the number of moles of gaseous reactants we have. Now here in the relation, we can understand mathematically, if delta N is greater than 0, then we can say that Kp is more than Kc. Delta N less than 0, we can say that Kp is less than Kc. And if at all delta n is equal to 0, then Kp must be equal to Kc. This can be understood mathematically from the reaction Kp is equal to Kc into RT power delta n. So delta n is equal to number of moles of gaseous products minus number of moles of gaseous reactants we have. So therefore units of Kp will be equal to C to the power of m d to the power of n by a power p b power q. All this m, n, q and p are nothing but stoichiometric coefficients in a balanced equation we have. So delta n will be equal to, that is a n plus m plus n we have, minus it is equal to p plus q, means number of moles of products, gaseous products, minus number of moles of reactants we have, that can be taken as delta n. Now if at all delta n is equal to 0, suppose if delta n value is equal to 0, then the Kp value becomes equal to Kc. Numerically both the values are same. Suppose delta n is not equal to 0, then the value of equilibrium constants will depend on the unit in which the concentrations are expressed. So if delta n is equal to 0, Kp and Kc have same numerical values. If delta n is not equal to 0, the value of equilibrium constant depends on the unit in which the concentrations are expressed. Regarding equilibrium constant we have. Equilibrium constant, some more points related to equilibrium constant. Equilibrium constant depends upon the temperature of the reaction and is given by log of K2 by K1 is equal to delta H by 2.303 R into 1 by T1 minus 1 by T2. Here K1 is equilibrium constant at temperature T1 and K2 is a equilibrium constant at a temperature T2 we have. So K1 at T1 temperature, K2 at T2 temperature we have. And here suppose if delta H is equal to positive, means in the case of endothermic reaction, and if at all T2 is say more than T1, then you can observe that the value of K2 will be also more than the value of K2 then now. For an endothermic reaction, if at all T2 is more than T1, then K2 becomes more than K1. K2 becomes more than K1 we have. And for an exothermic reaction, it is going to be opposite, means delta H is equal to negative, and if at all T2 is more than T1, then automatically what happens is K2 will be less than K1 we have. So remember, for an endothermic reaction, delta H is positive. At a higher temperature, you are going to get higher equilibrium constant. And independent of, it means equilibrium constant is independent of catalyst. Independent of catalyst because a catalyst speeds both forward as well as backward reactions to equal extent. Hence the ratio of K1 by K2 remains constant. So ratio remains constant because a catalyst speeds up both forward as well as backward reactions. Equilibrium constant is also independent of the concentration of reactants and products. Independent of concentrations because we are defining equilibrium constant. We are defining where the ratios K1 by K2 is also independent of the reactants as well as products, because the reaction rate constants are defined per unit concentrations of reactants. Equilibrium reaction rate constant is defined per unit concentration of the reactants, and thereby the value of is going to be independent of the reactants and products. Then comes per a given system, per equilibrium system, the numerical value of K depends on. Numerical value of K for a given system depends upon stoichiometry of a reaction. Stoichiometry of a reaction means, say for example, when you take reaction like A giving rise to B, suppose the value of K is equal to concentration of A divided by B here. Say for a reaction A giving rise to B here, equilibrium constant is given by concentration of B by concentration of A. Now, when you are multiplying say by 2, say 2A giving rise to 2B, then for this reaction say K dash will be equal to, it is going to be B square by A square then. Means if you are multiplying throughout by 2, the value of the new equilibrium constant becomes square of the previous one. So means K dash became equal to K square we have, multiplying throughout by 2. If I are dividing throughout by 2 means if I take say half of A giving rise to say half of B, then the new value of say K dash will be equal to square root of K we have. So dividing throughout by 2, we get root. We're going to get root of the previous K value. Multiplying throughout by 2, it will be squared. Dividing by 2, it is going to be root over that. So depends upon the stoichiometry of reaction also. Depends upon how we represent the reaction. Suppose if you take reaction like A to B, then equilibrium constant K is equal to concentration of B by A we have. If you represent the reverse way, means if I write it as say B giving rise to A, then K dash will be equal to concentration of A by concentration of B we have. So if we reverse the reaction, then equilibrium constant will become inverse of that. So now the new K dash became equal to 1 by K. So if we reverse the reaction, then equilibrium constant will become inverse of the previous one now. This is how equilibrium numerical value depends on. One more point, the importance of numerical value of K. Higher value of K indicates reaction almost all goes to completion. Say for example, value is very high, something like 10 to the power of 3, very higher value. It says that reaction almost all goes to completion. We have 10 to the power of 3 times the products we have, means reaction almost all goes to forward direction. The value of very much lesser value of K indicates, suppose the value is 10 to the power of minus 3, very much lesser value. It says reaction hardly proceeds. So the numerical value also gives the nature of reaction for us. Higher value says reaction almost all goes to completion. Very much lesser value says reaction hardly proceeds now. Now importance of reaction quotient. Reaction quotient formula and equilibrium constant formula remain same. Now importance of reaction quotient. If reaction quotient is less than K, then you can say equilibrium moves in forward direction. If reaction quotient is more than K, it moves in backward direction, and is equal to K means system is already at equilibrium state. So equilibrium reaction quotient, if it is less than K, equilibrium moves in forward direction, more than K moves in backward direction, less than K system is at equilibrium. Then comes the factors affecting the equilibrium. Affecting equilibrium, we can say position of equilibrium also there. So factors affecting the position. It depends upon the change in the concentration of reactants and products. When you change the concentration of reactants or products, then the position of equilibrium is going to be affected. How it gets affected, we are going to see after discussing Le-Chatelier's principle now. It also depends upon temperature and depends upon the presence of inert gas at a constant temperature, at constant pressure we have. So the position of equilibrium depends upon change in the concentration of reactants and that of products, depends on temperature, depends on addition of inert gas at a constant pressure, and it's going to be independent of, means this will not affect the position of equilibrium. That is presence of catalyst and addition of inert gas at a constant volume. These two are not going to affect the position of equilibrium. So three factors means the change in concentration, change in the concentration of reactants, product, and pressure, temperature, addition of inert gas at constant pressure. These will affect the position of equilibrium, and catalyst and addition of inert gas at constant volume, these will not affect the position of equilibrium. Then Le-Chatelier's principle. It says that if a system at equilibrium is subjected to change of concentration or pressure or temperature, then equilibrium shifts in a direction to minimize the effect of change. It states that at an equilibrium, if an equilibrium is subjected to change of concentration, of pressure or temperature, then equilibrium shifts in a direction to minimize the effect of the change. So from Le-Chatelier's principle, it follows that increase in temperature favors endothermic reaction. So endothermic reaction always requires energy. So thereby increase in temperature favors the endothermic reaction. Increase in the pressure favors the reaction which takes place with a reduction in the number of moles. Reduction in the number of moles here. Means for example, when you take a reaction like say A giving rise to 2B, in this case, if you are increasing the pressure, the reaction moves in backward direction, because in backward direction we have less number of moles are there. Suppose you have a reaction like 2A giving rise to B here now. Pressure is increased, it moves in forward direction, because in forward direction we have less number of moles. Suppose you have a reaction like A giving rise to B, both of them are gases, so pressure will not have any effect on that. So it says that the increase of pressure favors the reaction which takes place with reduction in the number of moles. So wherever the number of moles are less, reaction moves in that direction by increasing in the pressure. Addition of reactants or else removal of products favors the forward reaction. Addition of reactants, removal of products always favors the forward reaction. When forward reaction is favored, it means that equilibrium shifts to right side and we get more amount of product. So when we say forward reaction is favored, it implies that equilibrium shifts to right side and you are going to get more amount of product. That is the meaning of saying forward reaction is favored. So Le-Chatelet's principle says that if you are increasing the concentration of reactants or decreasing the concentration of the products, it moves in the forward direction. When you increase the temperature, it moves in endothermic reaction, means it favors the endothermic reaction. If the pressure is increased, it moves in a direction where you have less number of moles. Now examples of Le-Chatelet's principle. If you take an example of formation of nitric oxide, the reaction is endothermic in nature, and here delta N is equal to 0. Delta N value is equal to 0 in this case. Delta N 0 means there will not be any effect of pressure, and delta H is equal to plus Q means nothing but endothermic reaction. So therefore, higher the temperature means it moves in the forward direction. So high temperature, reaction moves in the forward direction. Then formation of ammonia is a exothermic reaction and number of moles are less on the product side now. So higher the pressure, it moves in forward direction, and lower temperature moves in forward direction. So therefore low temperature favors the formation of ammonia here, and number of moles are less in forward direction, thereby high pressure it moves in the forward direction. Then PCl5 formation, reaction is plus Q, means endothermic in nature, and number of moles of reactants are less, so high pressure moves in backward direction. So higher temperature, forward direction, higher pressure, backward direction we have. This is regarding the examples. Then comes chemical equilibrium topic. First of all, hydrolysis, the phenomenon in which a salt reacts with water to give slightly acidic or basic or neutral solution itself is called salt hydrolysis. The phenomenon in which salt reacts with water to give acidic, basic or neutral solution is known as salt hydrolysis. It is a reverse of the neutralization reaction. The neutralization reaction, acid and base react to form salt and water. Here salt and water reacting, hence can be considered to be a reverse of neutralization reaction. The salt of strong acid and strong base, something like say NaCl, salt of strong acid and strong base will not undergo hydrolysis. Therefore, their salt solutions always remain neutral. Salt of strong acid and strong base, something like NaCl solution, will not undergo hydrolysis, and thereby their solutions always remain neutral. For example, if you take a salt like AB, dissolved in water, first of all undergoes ionization, suppose giving A plus and say B minus now. Suppose if at all A plus is a strong conjugate ion, so A plus reacting with water, HOH, let us take H plus and OH minus. A plus will react with OH minus, it forms AOH and releasing here H plus ions, means the entire solution is going to be acidic in nature. Suppose B minus is strong conjugate ion, so B minus plus water, H plus and OH minus giving rise to, so these two react here, it forms HB, releases OH minus, and thereby it is going to be basic in nature. Suppose both of them react with water, you are going to get H plus as well as OH minus. In turn, these two combine, H plus and OH minus will combine to form water molecule. Then such a solution is going to be neutral. So thereby, the phenomenon in which salt reacts with water to give acidic, basic or neutral solution. So it is forming acidic here, basic here, or it can form even neutral also. The entire phenomenon is called salt hydrolysis. Now different types of hydrolysis we have. So that is hydrolysis of salt of strong acid and weak base. Strong acid and weak base. You can take strong acid means you can take HCl. Weak base you can take something like ammonium hydroxide. So their salt will be ammonium chloride here. Salt of say weak acid and strong base you can take. Weak acid you can take acetic acid here. Weak acid. And then say strong base you can take any OH here. Corresponding salt will be sodium acetate here. Salt of weak acid and weak base, if you take these two, and it's going to be ammonium acetate salt. These three salts undergo hydrolysis. So salt of strong acid, weak base, salt of weak acid, strong base, salt of weak acid and weak base. These three salts undergo hydrolysis, and salt of strong base and strong acid will not undergo hydrolysis. Let us take one by one. Now let us take hydrolysis of salt of strong acid and then weak base, say ammonium chloride. When you dissolve ammonium chloride in water, first of all it undergoes ionization. It gives rise to NH4 plus. It gives rise to NH4 plus and Cl minus ions here. Ammonium ions react with water and produce ammonium hydroxide plus H plus ions. Therefore, the solution is going to be acidic in nature. Ammonium ions plus water gives rise to ammonium hydroxide plus H plus. So, the solution is going to be acidic in nature. Now, it is also called cationic hydrolysis because here cation reacts with water, hence called cationic hydrolysis. Now, coming towards hydrolysis constant, Kh will be equal to product of ammonium hydroxide into it will be H plus by ammonium ion. We have product of ammonium hydroxide into H plus by NH4 plus ions will give us hydrolysis constant, which is called Kh. Now here hydrolysis constant is an equilibrium constant only for hydrolysis reaction of the salt. And when you say degree of hydrolysis is a number of moles of salt hydrolyzed per mole of salt itself is called degree of hydrolysis. Is represent as a symbol H here. It is called symbol as Kh for us now. So the Kh is the symbol used for the hydrolysis constant. H is a symbol used for the degree of hydrolysis. Let us take a salt of now strong base and then weak acid we have. That is when you dissolve sodium acetate, you are going to get here acetate plus sodium ions now. So here acetate ions react with water and produce OH minus ions. Therefore, the solution is going to be basic in nature. It will be basic in nature because of the OH minus ions. And it is called anionic hydrolysis because anion reacts with water. So it is called anionic hydrolysis. Hydrolysis constant is given by product of these two, acetic acid plus OH minus ions by acetate ions we have, where Kh is called hydrolysis constant. Then comes third salt, salt of weak acid and then weak base we have. When you dissolve, say, ammonium acetate salt in water, you are going to get acetate ions plus ammonium ions. Now here in this case, both react with water. Acetate as well as ammonium ions both react with water. And then finally you are going to get here. So acetate ions as well as means if you go back you can understand acetate ions react with water to form acetic acid here now. And then here ammonium ions from ammonium hydroxide here now. So thereby you are going to get in this case acetic acid plus ammonium hydroxide. But nature depends upon the Ka and Kb values. Suppose Ka is more, then it is going to be acidic in nature. If Kb is more, that is going to be basic in nature. Suppose both of them are equal, that is said to be neutral salt. And Kh is given by product of acetate ion concentration into NH4OH concentration by ammonium ions into CH3CO minus ions. It is called hydrolysis constant we have. Now let us take relationship between the hydrolysis constant, degree of hydrolysis and pH of respect to aqueous salt solutions we have. So type of salt, then Kh formula, then degree of hydrolysis, then pH formula of that. When you take salt of say strong acid and then weak base, strong acid and weak base, if you take suppose something like ammonium, say chloride here, ammonium chloride here now. So strong acid and weak base we have. When you have weak base, remember the KH formula, in the denominator we are going to get Kb of that one now. Kb will come. So Kw by Kb we have now. And if you take your weak acid here, so Ka comes. So for example, in this case you can take the example of sodium acetate you can take here. It is sodium acetate, salt. Salt of strong base and weak acid. So weak acid, so Ka comes here now. Here both of them are weak. It will be ammonium acetate salt. CH3COO, say NH4. When both are weak, so hydrolysis constant, denominator you are going to get both Ka and then Kb. So for the salt of weak base, so KH contains Kb here in the denominator. Salt of weak acid, Ka comes in denominator. Both are weak, both are coming in the denominator we have now. Then comes the hydrolysis constant, hydrolysis degree of hydrolysis formula. It will be root of KH by C. The formula remains same in both the cases. But in the case of salt of weak acid and weak base, this is independent of concentration of the salt. So H is independent of concentration of the salt. Simply root of KH we have. Then comes the pH formula. When you take salt of strong acid, the pH is going to be less than 7. So the formulas will be 7 minus will come. Less than 7. 7 minus pKb by 2 minus half log C. Both are minus and minus signs we have taken common here. If it is salt of strong base, the pH is going to be more than 7. Therefore 7 plus and plus will come in this case. 7 plus pKa by 2 plus half log C we have. When both of them are weak here, it will be 7 plus pKa by 2 minus it will be pKb by 2 we have. That way try to remember the formulas. And when both of them are strong acid and strong base, something like say NaCl salt, the salt never hydrolyzes and therefore formulas will not be there for salt of strong acid and then strong base we have. Then comes Ostwald's dilution law. It states that degree of dissociation of a weak electrolyte is proportional to square root of dilution, is directly proportional to square root of dilution. Let us take a salt or electrolyte like AB giving rise to A plus B minus, C initial concentration 0 and 0. Say at equilibrium C minus C alpha we have. So equilibrium constant K is equal to C alpha square by 1 minus alpha comes. If it is very much weaker electrolyte, 1 minus alpha can be taken as nearly equal to 1. In such a case, K becomes equal to C alpha square then now. K is C alpha square. So therefore, alpha square is equal to K by C. Alpha is equal to square root of K by C we have. And we know that concentration is inversely proportional to volume. Therefore, alpha is equal to square root of K into V it comes. This implies alpha, that is a degree of dissociation, is directly proportional to root of V we have. Square root of the volume itself is called Ostwald's dilution law. By applying this law, so the formula is alpha square C by 1 minus alpha. By applying Ostwald's dilution law for a weaker acid and weaker base, we are going to get formulas H plus is equal to root of KAC. H plus will be equal to C alpha, also equal to square root of K into C will come. Similarly, for a weaker base, OH minus will be equal to C into alpha, or else root of KB into C. Here Ka and Kb are dissociation constants of weaker acid and then weaker base we have. And the value of Ka, Kb is higher means it is going to be a stronger acid. So Ka, Kb are higher values implies that there is going to be a stronger acid. And pKa is given by minus of log Ka and pKb is called minus of log Kb we have. And if at all smaller the value of pKa and pKb, the acid strength and base strength will be higher now. So smaller the value of pKa, stronger the acid. Smaller the value of pKb, stronger the base we have. So higher value of Ka or smaller value of pKa will be stronger acid. As regarding Ka, pKa. Then comes common ion effect. Now it is defined as the decrease in the dissociation of a weak electrolyte in the presence of common ion containing substance is called common ion effect. The decrease in the dissociation of a weaker electrolyte in the presence of a common ion containing substance. For example, when you take, say, dissociation of acetic acid, say weaker electrolyte, acetic acid dissociates, use here CH3COO minus plus H plus we have. Suppose when you take a common ion containing substance, something like say acetic acid, sodium acetate here now, it ionizes completely, we are going to get acetate ions plus sodium ions. Now if you see here, is giving acetate ions are there. So here already we have acetate ions now. So sodium acetate increases the concentration of acetate ions here. So when these ions are increasing here, the above equilibrium moves in backward direction. Implies the concentration, implies the dissociation of acetic acid is going to be reduced now in the presence of common ion containing substance. So decrease in the dissociation of weak electrolyte in the presence of common ion containing substance itself is called common ion effect we have. If we take one more example like ammonium hydroxide, say ammonium hydroxide, it is a weaker electrolyte giving rise to, it forms ammonium ions plus OH minus ions. Add common ion containing substance like ammonium chloride giving rise to ammonium ions plus Cl minus ions here. We are again adding common ion containing substance. Thereby this moves in the backward direction. Hence you can see decrease, we can see the decrease in the dissociation of ammonium hydroxide ionization. So we can see decrease in the dissociation of weak electrolyte in the presence of common ion containing substance, which itself is called common ion effect. Then comes the solubility product. Molar is defined as product of molar concentrations of constituent ions raised to the power equal to its stoichiometric coefficients in the equation representing dissociation of electrolyte at a given temperature in a saturated solution. Product of molar concentrations of constituent ions raised to the power equal to stoichiometric coefficients in the equation representing dissociation of electrolyte at a given temperature itself is called solubility product. Implies, let us take a compound like BaCl2. Let us take saturated one solution giving rise to Ba plus 2, say aqueous solution plus Cl minus here. Aqueous solution we have. So here it is representing the dissociation of a weak dissociation of an electrolyte here now. Now the Ksp of BaCl2 is equal to, it is a product of ionic concentrations of Ba plus 2 and Cl minus raised to the power of the respective coefficients now. Means it will be concentration of Ba plus 2 into it will be concentration of Cl minus to the stoichiometric coefficient is 2 we have now. So this itself is called now Ksp of BaCl2. Product of molar concentration of constituent ions. Molar concentration of constituent ions raised to the power here equal to stoichiometric coefficients in the equation representing the dissociation of an electrolyte in the presence of electrolyte at a given temperature. Next, product of solubility product principle now. If ionic product exceeds Ksp, then we can see precipitation taking place. So ionic product and Ksp have similar formulas. So Ip comes at a different conditions now. So Ip exceeds Ksp, then we can see formation of precipitates. If ionic product is less than Ksp, no precipitate is being formed. Even equal to also, we cannot see precipitation forming. So condition of precipitation is the ionic product must be always greater than the Ksp value. Then the formula for Ksp. Suppose if you take a salt like AxBy, for a salt like AxBy, giving rise to say X moles of A, say plus Y, plus say Y moles of say B minus X you have, B minus X. Now Ksp is given by, means KSP of AXBY. AXBY is given by product of molar concentrations of the ions. So A plus raised to the respective coefficients. Power will be coefficients here. B minus X to the power of Y we have. This is said to be KSP. And if at all S is a solubility, if S is a solubility, then KSP for any salt in general can be given by X power X, Y power Y, and S to the power of X plus Y we have. If S is a solubility and X and Y are respective coefficients, we can say X power X, Y power Y, S to the power of X plus Y. Let us take few examples here. For a salt like AgCl, so S square means Ag plus into Cl minus will come, S square will come. For BaCl2 it will be Ba plus 2 into it will be Cl minus whole square will come. Cl minus square will come, and Cl minus square means it will be 4 then now. Because Ba plus 2, 2Cl minus will come. So 4S cube will come. In the case of quaternary salt, something like AlCl3 where ions altogether are 4 in number, it will be 27S to the power of 4 we have. So we can apply the formula. For these things we can apply the formula X power X, Y power Y, S to the power of X plus Y we have. Then the theories of acids and bases, Bronsted-Lowry theory. So proton donor or protogenic substance is called acid. Proton acceptor or protophilic substance is called a base. Suppose when you take HCl plus water, in this reaction, say it is H3O plus Cl minus now. HCl is giving proton, so this can be called as an acid. Water takes proton from HCl, so water can be called as base in Bronsted-Lowry theory in this reaction. And meaning of conjugate acid-base pair. A pair of acid and base which are differing by a proton itself is called conjugate acid-base pair. Pair of acid and base differing by a proton. It's called conjugate acid-base pair. Suppose when you take a substance and add a proton, you are going to get corresponding acid. Add a proton, you are going to get corresponding acid now. If you remove a proton, you are going to get corresponding base. Let us see in examples now. Say ammonia plus H plus gives ammonium ion for us now. Ammonia base adding a proton, we are going to get ammonium ion, going to be corresponding conjugate acid then now. Water adding a proton, you are going to get hydronium ion. So water and hydronium ion will make corresponding conjugate acid base pair. But in this, H3O plus is going to be acid, H2O is going to be base for us. Similarly, H3O plus adding proton, you are going to get corresponding acid we have. So HSO4 minus plus H plus, H2SO4 corresponding acid we have. So if you remove, we are going to get corresponding base. So water minus H plus corresponding base we have. OH minus H plus, you are going to get corresponding the base. So you remove proton, you get a base. Add a proton, you are going to get corresponding acid. This is a conjugate acid-base pair you have. And then one more important point. In a conjugate acid-base pair, if the acid is stronger, corresponding base is going to be weaker. In a conjugate acid-base pair, if acid is stronger, corresponding base is weaker. And if base is stronger, corresponding acid is weaker. We have in conjugate acid-base pair, one will be strong and then one is going to be weaker and vice versa. This is regarding conjugate. Next, Lewis concept of acids and bases. Here electron pair acceptor is called acid. Electron pair donor is supposed to be a base for us. So when you take a reaction like say NH3 giving electron pair to say BF3 molecule in some reaction. In this reaction now, here BF3 electron pair acceptor is called acid here. Donor is called base in this case. So electron pair donor is base and is called acid now. So therefore, we take examples of Lewis acids here. All neutral molecules with less than octet around central atom, because they are going to accept electron pairs. Neutral molecules having less than octet around central atom will be Lewis acids now. We can take all cations with vacant orbitals. Cations having vacant orbitals also accept electron pairs now. So they are also Lewis acids now. And molecules which can expand octet configurations. They may have octet or more than octet, but if they are in position to expand octet further, they also take electron pairs, hence act as a Lewis acids. So molecules which do not have octet, which have vacant orbitals, which can expand octet, will come under Lewis acids. When it comes to base, neutral molecules with one or more lone pair of electrons in central atom. So when you take all amines here, primary, secondary, tertiary, they have a lone pair upon the nitrogen, so they can donate lone pair, hence they are Lewis bases we have. And anions which can donate one or more lone pair also act as a Lewis bases. Suppose when you take a reaction like K4FeCN6, compound like K4FeCN6. In this compound, F is in +2 state now. Cn is in -1 state we have now. Each Cn minus ion donates electron pair to Fe+2 now. So in complete complex here, so Fe+2 is electron pair acceptor. Electron pair acceptor is called Lewis acid now. So this acts the role of Lewis acid. Electron pair donor, each Cn minus is called a base there now. So electron pair donor. So all ligands in a complex will be acting as a Lewis base. And central atom or ion is acting as a Lewis acid now. Regarding Lewis acid base theory we have. Then comes concept of pH. So pH is defined as negative logarithm of hydrogen ion concentration. Similarly, pH is also called negative logarithm of OH minus ion concentration, and pH plus pH is equal to 14. This will be at 25 degrees Celsius. And pH plus pH is equal to pKw here. And then pKa plus pKb is also equal to pKw is equal to 14 for us. This is for a given conjugate acid base pair, pKa plus pKb is equal to 14. Then pH plus pOH, some relations we have. Suppose H plus is given as, say, 10 to the power of -3. Then pH will be equal to 3 now. So 10 to the power of -n we have, pH becomes equal to n. So 10 to the power of -3, pH is equal to 3 we have. Suppose somewhere H plus is given as excuse me, say 2 into 10 to the power of -3 then the pH will become equal to 3 minus we have log 2 then 3 minus log 2. So it is x into 10 to the power of -n we have. See the same thing here. It is going to be n minus log x here. N minus log x, like this term, it is 3 minus log 2 we have. Similarly, we can take even for OH minus ion also, the same formula can be applied here now. And H plus will be equal to anti-log of minus pH. Anti-log of minus pH. So H plus is 10 to the power of -3. Therefore, the pH, suppose you have pH is equal to 3. What is the value of H plus? That is going to be anti-log of -3 then now. So if pH is equal to 3, from this H plus will be equal to anti-log of -3. This becomes 10 to the power of -3 then now. Similarly for OH minus ion also. Now ionic product of water. The product of ionic concentrations of H plus and OH minus itself is called ionic product of water. The value is constant only at 25 degrees Celsius. So it depends upon temperature. Higher the temperature, higher the concentration of H plus and OH minus, thereby the product also increases. And if it decreases, we are decreasing the temperature. Depends upon temperature. The product of H plus and OH minus of a water itself is called, or any aqueous solution itself is called ionic product of water. Then comes the buffers, Henderson equation we have. The pH of buffer consisting of a mixture of weaker acid and corresponding salt of strong base. So when you take CH3 COOH plus CH3 CONA, this mixture acts as a buffer. So mixture of weaker acid plus corresponding salt of strong base. Given by the formula pH is equal to pKa plus log of concentration of salt by acid. When you take the basic buffer, which is a mixture of weak base and corresponding salt of strong acid, you can take the example of weak base plus ammonium chloride here. This mixture you can take in this case. So the basic buffer pOH will be given as pKb plus log of concentration of salt by concentration of the base we have. And we know that buffer resists the change in the pH by adding a small amount of acid or else base even upon dilution we have. Even the aqueous solution of salt of weak base and weak acid also means, for example, when you take the compound CH3COONH4. Only the solution of this salt itself also acts as a buffer. So buffer will be mixtures like weak acid plus corresponding salt of strong base, weak base plus corresponding salt of strong acid here. Also it can be only aqueous solution of weak base and weak acid also acts as a buffer solution. Then today we will discuss important points from hydrogen and its compounds. Let us see where hydrogen can be placed in the periodic table. That is, position of hydrogen in periodic table. Hydrogen can be placed in group 1 or group 17. This we need to discuss now. Now, alkali metals are having NS1 configuration. Hydrogen is having 1s1 configuration. Both are having similar configurations now. Like alkali metals forming M plus ion, hydrogen also forms H plus ion. It forms cation of H plus. Like alkali metals form oxides, halides, sulfides, even hydrogen also forms oxides, halides, sulfides. So these 3 points are similar to that of alkali metals. Now, but in terms of ionization energy and electronegativity, hydrogen resembles halogens now. But in terms of IE and EN, it is resembling halogens now. Like halogens means X2 here, hydrogen forms diatomic molecule. It is forming H2. It forms diatomic molecule H2, which is similar to that of halogen now. Like halogens, hydrogen forms large number of covalent compounds. There are many covalent compounds for halogens as well as for hydrogen now. But it has low reactivity when compared to that of halogens. Because of strong bond energy in H2 molecule, it is having low reactivity when compared to halogens. And H plus is extremely small. H plus ion is extremely small. It is always associated with other atoms or other molecules. So for example, when you take H plus in aqueous solution, doesn't have any free existence. It is existing always as hydronium ion only, H3O plus. So H plus is extremely small and is always associated with other atoms or molecules. Thus, it is unique in behavior and therefore it is best to place hydrogen separately in the periodic table. It is having unique behavior and therefore it can be placed separately in the periodic table. Now let us see the isotopes of hydrogen. Isotopes of hydrogens. There are 3 isotopes. So 1H1, which is called normal hydrogen, also called protium. 1H2 called heavy hydrogen, also called deuterium. 1H3 also called radioactive hydrogen, which is called tritium. All differ in the number of neutrons present and all have same electronic configuration because all the 3 are isotopes. So hydrogen has 3 isotopes: normal hydrogen, heavy hydrogen, and then it is radioactive hydrogen. Then comes preparation methods of dihydrogen or called hydrogen. First one is action of zinc on HCl gives rise to H2 gas, also forms ZnCl2. Preparations of H2, action of zinc with dilute HCl gives H2 gas. Even action of zinc on aqueous alkali, that is sodium hydroxide, also produces H2 gas here. And the compound is Na2ZnO2. This is called sodium zincate. Sodium zincate is being formed here. So action of zinc on HCl, acid or sulfur or else NaOH will give rise to H2 gas. Then electrolysis of acidified water using platinum electrodes also gives us H2 gas. Now here hydrogen gas is formed at cathode and oxygen is formed at anode. Because H2O gives rise to H plus and then OH minus. H plus being cations move towards cathode, reduction takes place and thereby you are going to get H2 gas at cathode, and then OH minus ions, anions move towards anode, oxidation takes place, there we are going to get oxygen gas. Then comes high purity. high purity of dihydrogen gas is obtained by electrolysis of warm aqueous barium hydroxide. Warm aqueous barium hydroxide solution. That is here warm aqueous solution because to increase the conductivity of that. And using nickel electrodes, we are going to get high purity of dihydrogen gas by electrolysis of warm aqueous barium hydroxide using nickel electrodes. Reactions will be similar in nature. Then by electrolysis of brine solution also gives rise to H2 gas. H2 gas it forms. That is to say, NaCl gives Na plus and Cl minus. Cl minus ions being anions move towards anode. Their oxidation takes place and then you are going to get chlorine gas now. When it comes to at cathode water is getting reduced and finally it's going to liberate H2 gas. So liberation of H2 takes place at cathode because water gets reduced. So at anode, Cl minus ions are getting oxidized. There you are going to get chlorine gas, and at water, that is water, at cathode water is getting reduced and thereby we get H2 gas at cathode. Then comes reaction of steam with hydrocarbons or coke at high temperatures in the presence of a catalyst. Actually we are going to get here water gas from this. So we get water gas, that is steam with hydrocarbons or coke at high temperatures will give us water gas. From water gas we can prepare H2 gas. We can prepare H2. So hydrocarbon with steam at very high temperature, steam is used here at very high temperature, we are going to get mixture of CO and H2. CO and H2 itself, mixture itself is called water gas or synthesis gas or syn gas. Once you get mixture of these two here, we can separate carbon monoxide and get hydrogen gas. It is prepared from coal. It is prepared from coal also by a process called coal gasification. It can be prepared from coal by a process called coal gasification. These are the methods for the preparation of H2. Then coming towards properties, it is highly stable because of strong bond in that and less reactive due to the HH bond dissociation enthalpy. So it's highly stable because of strong bond that is present in H2 molecule. Atomic hydrogen is produced at high temperature in an electric arc or under ultraviolet radiations. So when you take H2 gas and heat it to very very high temperatures or else use electric arc, it is going to split up into two hydrogen atoms here and they are called atomic hydrogen. They are highly reactive in nature. Atomic hydrogen can be produced at high temperature in an electric arc or else under ultraviolet conditions. Then coming towards chemical reactions of hydrogen. Hydrogen reacts with the halogens to produce hydrogen halide H2 plus X. All are simple reactions here. H2 plus X2 giving rise to HX. It reacts with oxygen gas here, forms H2O, H2 plus O2 forming H2O. It is highly exothermic in nature. Then coming towards, it reduces metals in aqueous solutions and metal oxides which are having less active than iron. Less active than iron. Metals must be less active than iron, then it will be reducing to corresponding metals now. First one is reaction say with nitrogen. If you take, it is going to form ammonia gas, forms ammonia gas, and reaction with metal ions, when you consider here metal ions, metals, it forms metal hydrides. So with metals it forms metal hydrides here, and it even reduces metal ions or else even metal oxides to corresponding metals, but metal oxides must have less active metal when compared to that of iron. Then the reactions are shown as follows. So reactions with metal ions and metal oxides here. So H2 with metal ion must be less active when compared to iron here. Metal ion is changing into corresponding metal. You can take even metal oxide also using hydrogen here. Metal oxide gets reduced to metal here, provided metal must be less active when compared to that of hydrogen here. So therefore, it reduces metal ions or metal oxides to corresponding metals if at all metal is less active when compared to iron. Then with organic compounds, it reacts with many organic compounds. So hydrogenation of vegetable oils gives edible fats also called ghee, and hydroformylation of alkenes basically give us aldehydes now. Hydroformylation of alkenes will give us aldehydes, and aldehydes on further reduction with H2 will give us alcohol. Aldehydes further reduction will give rise to alcohol. Let us see the reaction here. So hydroformylation of alkene. So H2 plus CO used for hydroformylation reagent, this one. So alkenes are becoming now aldehydes, CHO aldehydes. These aldehydes on further reduction with H2, finally we are going to get alcohols. So we can say hydroformylation of alkenes. Finally you are going to get corresponding alcohols are being produced by hydroformylation reaction. These are the reactions of hydrogen. Then comes uses of hydrogen. It is used in the synthesis of ammonia by a process called Haber's process. In Haber's process, ammonia is being synthesized. In the preparation of nitrogenous fertilizers also, basically hydrogen can be used. In the manufacturing process of HNO3 also, H2 is used now. Then comes in the manufacturing process of Vanaspati, nothing but ghee. The process is hydrogenation of vegetable oils, leads to formation of Vanaspati. Manufacture of methyl alcohol, that is CO plus 2H2, in the presence of cobalt catalyst, you are going to get methyl alcohol. It is used in the manufacturing of even metal hydrides also. So mainly Haber's process, preparation of ammonia, HNO3, nitrogenous fertilizers, and hydrogenation of vegetable oils to get Vanaspati or ghee, preparation of alcohols, preparation of metal hydrides, and preparation of even HCl also, H2 plus Cl2 gives us HCl there, for reduction of heavy metal oxides in metallurgy to reduce heavy metal oxides to metal, where metal oxide must be less active than that of iron. And then in cutting and welding purpose also, atomic hydrogen can be used in the form of atomic hydrogen torch, or else even called oxyhydrogen torch here, because they are going to give us higher heat of combustion. So for welding and cutting purpose, atomic hydrogen torch or oxyhydrogen torch can be used, and used as a even rocket fuel in space research, and in the preparation of fuel cells especially hydrogen fuel cell, for generating electrical energy, it can be used. These are the uses of dihydrogen. Then comes classification of hydrates now. Hydrates are basically classified into three categories, that is ionic hydrates, sometimes called salt-like hydrates also, molecular, or you can call them as covalent type of hydrates, metallic, or else it can be non-stoichiometric type of hydrates. Hydrates are classified into three categories: ionic hydrates, covalent hydrates, and then metallic hydrates we have. Let us take one by one. First one, ionic hydrates. Hydrates of S block elements except beryllium and magnesium are the ionic hydrates we have. This beryllium and magnesium are coming under covalent type of hydrates, and this beryllium hydride, that is BeH2, and magnesium hydride MgH2, these two molecules are having polymeric structures. So these two have polymeric structures and they are covalent in nature. So except beryllium and magnesium, all other S block elements form ionic type of hydrates, and these hydrates have the properties of ionic compounds itself. So they are ionic hydrates and they have properties of ionic compounds. So their melt means when you take the molten solution of ionic hydrates on electrolysis, they are going to give us H2 gas at anode. Means when you take, for example, sodium hydride. So sodium hydride on electrolysis, it first of all ionizes to form Na plus it forms H minus. H minus is anion here, and then it is being formed, it moves towards anode. There it's undergoing oxidation. So H minus, 2H minus gives rise to H2, liberation takes place, plus 2 electrons we have now. So therefore here at anode only we are going to get H2 gas because hydride ions are being produced, that is on electrolysis of sodium hydride. And then it reacts violently with water. Suppose when you take reaction between sodium hydride plus H2O, it reacts to form sodium hydroxide plus H2 we have. Under this heading, we have a compound called CH2, which is commercially known as hydrolith. used for the commercial production of even hydrogen gas also. Hydrolyte also, with water it forms calcium hydroxide plus it is H2 gas we have. So the melt on electrolysis forms H2 gas. Important thing is that H2 gas is formed at anode, not at cathode there. They react violently with water. Commercially important compound is CH2, which is called hydrolyte, will produce H2 gas upon dissolution in the water. These are the covalent type of hydrates. Then the hydrates of P block, so these are the ionic type of hydrates. Then hydrates, the covalent type of hydrates of P block and the beryllium and magnesium of S block will form covalent hydrides. Hydrates of P block and that of beryllium and magnesium will form covalent type of hydrates. Examples are CH4, ammonia, H2O, HF, etc. The covalent hydrates are further classified into electron deficient hydrides, electron precise hydrides, electron rich type of hydrides, depending upon number of electrons around central atom. So depending upon number of electrons around central atom, these covalent hydrides are further classified into three categories. They are electron deficient hydrides, electron precise hydrides, electron rich hydrides we have. Let us take now one by one, say electron deficient type of hydrides here now. 13th group elements form electron deficient type of hydrides. They are called electron deficient because they have less number of electrons than octet around the central atom. They have less number of electrons around central atom, less number than that of octet configuration. So when you take AlH3 molecule, we have only 3 bonds present here. AlH3 means 3 bonds includes us 3 bonds means we have only 6 electrons around aluminium. It is having 2 electrons less than that of octet configuration. So therefore, these molecules will be acting as Lewis acids because they are electron deficient in nature. So electron deficient hydrides, 13th group elements are forming electron deficient hydrides. They are called electron deficient because they have less number of electrons than octet around the central atom. Then comes electron precise hydrides now. 14th group elements form electron precise hydrides now. They are called electron precise because they have octet around the central atom. They have exactly octet configuration around central atom. Therefore, they are called electron precise hydrides there. So examples are CH4, that is methane, SiH4, silicomethane, and so on and so forth. Means 14th group hydrides have octet around central atom. Therefore, they are called electron precise hydrides. Then electron rich hydrides now. 15, 16, 17th group elements form electron rich type of hydrides now. They are called electron rich because they have one or more lone pair of electrons to share. They are having one or more lone pair of electrons to share, and therefore they are called electron rich type of hydrides. So when you take ammonia, ammonia has one lone pair of electron on nitrogen. If you take water molecule, water has 2 lone pairs on oxygen atom. So therefore, these lone pairs can be shared by others. So they are electron rich. So 15, 16, 17 group elements form electron rich hydrides, and they are electron rich because they can share one or more lone pair of electrons to other species. These are all called covalent type of hydrides. Next comes metallic type of hydrides here. Hydrides of D and F block elements are called metallic type of hydrides now. They are having the same properties as that of metals itself. They conduct heat as well as electricity, which are the properties of metals itself only. They are also known as non-stoichiometric type of compounds. They do not have general formula, so they are called non-stoichiometric type of compounds. They will not have any whole numbers there. For example, a lanthanum hydride is having 2.87H. It implies that 1 mole of lanthanum will be having 2.87 moles of hydrogen with lanthanum there. Similarly, when you take nickel hydride, is having a ratio, range is there. So 1 mole of nickel can be associated with 0.6 moles of hydrogen or even 0.7 moles of hydrogen. We have a range between those two. Hence, they are called non-stoichiometric type of compounds. That is, you do not have any fixed molar ratio. Earlier, they are also called interstitial hydrides. That is, the metallic hydrides are also known as earlier interstitial hydrides. Now, metals like platinum and palladium can accommodate large volume of hydrogen in their interstitial sites. Metals like platinum and palladium can accommodate large volume of hydrogen in their interstitial sites. Therefore, they can be used for the storage of large volume of hydrogen. They are used for storage of large volume of hydrogen. They can be used as a source of energy also. They can be used as a source of energy. This is regarding metallic type of hydrides. With this we have done the different type of hydrides. Hydrides we have done ionic hydrides, covalent hydrides, and then metallic hydrides we have. Then the next is compound is water. In the gas phase, H2O is having bend-shaped molecule. It is a bend-shaped molecule. When it comes to solid state, which is nothing but ice, ice has highly ordered three-dimensional hydrogen bonded structure. Highly ordered three-dimensional hydrogen bonded structure. And each oxygen atom is surrounded tetrahedrally by 4 other hydrogen atoms. 2 of them are hydrogen bonded and 2 of them are covalent bonded there. So each oxygen atom is surrounded tetrahedrally, means having 4 bonds, tetrahedrally by 4 other hydrogen atoms. In 4 hydrogen atoms, 2 of them are hydrogen bonded and 2 of them are covalent bonded with with oxygen atom. Then coming towards properties of water we have. It is a universal solvent because of very high dielectric constants. Therefore, ionic compounds as well as covalent compounds can dissolve in water due to its high dielectric constant. Hence, it is called universal solvent there. It is amphiprotic in nature. It is amphiprotic means it can act as both acid as well as base. It has ability to act as both acid as well as base. Let us take examples for this. Suppose when you take water and with HCl, this will be HCl donates proton to water. It forms H3O plus Cl minus. So in this reaction, water is accepting proton from HCl now. So what is a proton acceptor? Is acting as a base now. But when you take a reaction of H2O with ammonia, giving rise to ammonia accepts proton from H2O. It is forming NH4 plus and OH minus. So in this reaction now, what is donating proton to ammonia? Therefore, what is acting as a acid here now? So in the first reaction, water acts as a base. Second reaction, water acts as an acid now. Such a species is said to be amphiprotic species now, which can act as both acid as well as base. It undergoes autoprotolysis. Autoprotolysis, that is nothing but self-ionization to give hydronium ion as well as OH minus ions in aqueous solution. It undergoes autoprotolysis, nothing but self-ionization. Suppose when you take water alone, say let us take separately. For convenience, I am writing like this, H2O plus H2O giving rise to. So here, one gives proton to other one now, implies you are going to get there H3O plus we have here OH minus, which is said to be autoprotolysis or nothing but self-ionization. Means we are going to get hydronium ions plus OH minus ions. Then, properties of water. Many salts, when dissolved in water, can be crystallized as hydrated salts. Many salts, when dissolved in water, can be crystallized as hydrated salts. And there are different types are there in hydrated salts also. Let us take one by one. Suppose you take in some cases, water forms coordinate covalent bonds with the central metal ion, something like say chromium here. Actually, it should be Cr H2O taken 6 times Cl3 now. In this complex here, water is forming coordinate covalent bond with the chromium ion Cr plus 3 now. So in some cases, water forms coordinate covalent bonds. So we can say it's a coordinated water molecules are there in this complex now. In some cases, water occupies interstitial sites of the crystal structure of the salt. In some cases, water occupies interstitial sites of the crystal structure of the salt. For example, in the case of BaCl2, BaCl2H2O. The 2H, that is water molecules, are occupying the interstitial sites of BaCl2 molecule there. So that's said to be interstitial water, where the molecules are occupying the interstitial sites in the BaCl2. And in some cases, it forms hydrogen bonds. In some cases, it forms hydrogen bonds. When you take your copper sulfate here, so in copper sulfate pentahydrate molecule, which is blue in color, in this entire structure here, copper is coordinated with 4 water molecules, and sulfate forms hydrogen bond with 1 water molecule. Sulfate forms hydrogen bond with 1 water molecule. So in altogether 5 water molecules in copper sulfate pentahydrate, 4 of them are coordinated with copper ion, and 1 forms hydrogen bond with sulfate ion. So therefore, when salts are crystallized, we are going to get hydrated salts, and there are different types are there. In some cases, water exists as coordinated water molecules, some cases interstitial water molecules, some cases hydrogen bonded water molecules we have. Then hard water and soft water. That is water which is not giving any foam or lather with soap itself is called hard water. Hard water does not give lather or foam with soap. That is because of the presence of dissolved calcium and magnesium salts in it. So hard water forms precipitate with the soap. Soft water gives lather with soap. So the water which is not producing lather with soap itself is called hard water. Let us take, for example, if you take a soap molecule, say sodium stearate molecule, so C17H35CONA, soap molecule, or called sodium stearate molecule. When you take hard water which contains, say, calcium or say magnesium ions, which are there in hard water, these are there in hard water. So we have hard water containing these two. Then what happens is, you are going to get a precipitate of stearate of calcium or magnesium. So therefore that is C17H35COO taken twice. It will be calcium here, or it can be even magnesium also there. So magnesium or calcium stearate is being formed. This is a precipitation. So if at all hard water, that is hard water containing calcium and magnesium ions are there, if soap is being used here, you are going to get precipitate of calcium or magnesium stearate. So therefore soap will not produce any lather if at all water contains calcium or else magnesium ions in them. Then different type of hardness and comes how to remove the hardness. So temporary hardness is because of basically bicarbonates of, it will be calcium and magnesium ions. Calcium and magnesium bicarbonates are there. And permanent hardness is because of, it will be chlorides and then say sulfates of calcium and then magnesium ions. So temporary hardness is because of bicarbonates of calcium and magnesium, and permanent hardness is because of chlorides, sulfates of calcium and then magnesium we have. So temporary hardness is presence of magnesium and calcium hydrogen carbonates, nothing but bicarbonates we have. So let us see how to remove first of all the temporary hardness. It can be removed by following methods. First one, boiling. So when you are boiling the hard water which is containing magnesium bicarbonate, on heating it dissociates to form magnesium hydroxide as precipitation here and liberates carbon dioxide gas. So magnesium bicarbonate dissociating into magnesium hydroxide, which is a precipitation that can be removed. If at all the water contains say calcium bicarbonate, it forms a precipitate of calcium carbonate and then water plus carbon dioxide gas we have. So calcium and magnesium bicarbonates are becoming here magnesium hydroxide precipitate, or it can be calcium carbonate as a precipitate. That way we can remove those precipitates. So finally you are going to get soft water. In Clerk's method is addition of required amount of lime. We are adding there required amount of lime to remove temporary hardness, which is called Clerk's method. So calcium bicarbonate, nothing but temporary hardness, plus lime being added, you are going to get once again precipitation of calcium carbonate, which can be removed. And if at all you have magnesium bicarbonate as a hardness containing compound plus lime here, calcium hydroxide, you are going to get calcium carbonate plus magnesium hydroxide. Once again, both of them are precipitates only. So by adding required amount of lime also, we can remove temporary hardness. That is, you are converting bicarbonates into respective carbonates and hydroxides, which are precipitates, and they can be removed completely. Then comes permanent hardness. It is because of the presence of dissolved magnesium chloride, that is calcium chloride, magnesium sulfate, and calcium sulfate. Means nothing but chlorides, sulfates of magnesium and then calcium. This result in the permanent hardness, which cannot be removed by simple boiling there. Now, how to remove the permanent hardness? Different methods are there. First of all, treating with the washing soda, that is sodium carbonate, we have Colgan's process, ion exchange method, and then we have synthetic resin process. 4 different methods are there: washing soda, Colgan method, ion exchange method, and we have synthetic resin method we have. Let us take first one, that is a treatment with washing soda. Suppose you have a hardness containing compound, let's say calcium chloride. So permanent hardness causing compound, calcium chloride of calcium. When you add for this washing soda, that is Na2CO3, then it forms here calcium carbonate, which is precipitation that can be removed here and forms NaCl. Suppose you have a sulfate also, the same reaction takes place there now. Suppose you have calcium sulfate, adding here says again washing soda, Na2CO3, giving rise, it forms once again here calcium carbonate, it forms CaCO3 as a precipitation, plus it will be Na2SO4 here now. So therefore you are converting chlorides and sulfates as a calcium carbonates, which are precipitates there. Similarly, you can use for magnesium chloride or magnesium sulfate also. So by adding, you are converting the calcium ions into corresponding carbonates, which can be removed. Then comes Colgan process. Colgan is a sodium hexametaphosphate, that is NaPO3 taken 6 times. Sodium hexametaphosphate. Sodium hexametaphosphate itself is called Colgan. Here Colgan, calcium and magnesium ions, which are present in hard water, will form a complex with the Colgan. That way calcium and magnesium ions can be removed. So Colgan is sodium hexametaphosphate, NaPO3 taken 6 times. The calcium and magnesium ions which are present in hard water will form complex with it, and therefore they can be removed. Now when it comes to ion exchange method, which is also called permutate or zeolite process, it contains a sodium aluminum orthosilicate. It can be written in short as NaAlSiO4. NaAlSiO4, sodium aluminum, it is orthosilicate, and can be represented in short form as NaZ. It is called sodium zeolite. So now the hard water that is having calcium or else magnesium ions, if you are passing through sodium zeolite, say here sodium zeolite, so NaZ, sodium zeolite, then here the sodium ions are replaced by calcium and magnesium ions of hard water. We are going to get here sodium ions plus it will form here calcium, that is Ca, it forms Z2, or it can be MgZ2 will form, means calcium, or else you are going to get magnesium zeolite. So sodium zeolite means permutate is changed into calcium or else magnesium zeolite, and leaving Na plus ions in water. In that way we can remove calcium or else magnesium ions which are there. So hard water, when it is being passed through zeolites, sodium zeolite, you are going to get here calcium and then magnesium zeolite here. And these calcium and magnesium zeolites can be revived by passing brine solution through that. Suppose you have calcium zeolite, CaZ2, or you have say magnesium zeolite, which is called exhausted zeolites here. By passing here brine solution, means NaCl, we can get back the sodium zeolite which can be used. So in that way we can revive the exhausted zeolite also. So when you are passing hard water through zeolites, that is sodium zeolite, we are going to get calcium or else magnesium zeolites. Again when you pass brine through the exhausted zeolites, we can get back the sodium or else sodium zeolite. This is regarding ion exchange method you have. When it comes to synthetic resin method, synthetic resin contains cation exchange resin as well as anion exchange resins. Resins are organic polymers having acidic and basic groups now. So two are there, cation exchange resin as well as anion exchange resin we have. In cation exchange resin, H plus exchanges for Na plus, Ca plus 2 or Mg plus 2. So all cations are exchanged for H plus ions now. So in the place of all cations, you are going to get H plus ions. That is when you are passing water through cation exchange resin. So in cation exchange resin, all cations are blocked. You are going to get the H plus ions from that. When you pass hot water through anion exchange resin, the anions of hot water are blocked and finally you are going to get their OH minus ions. So through anion exchange resin, we get OH minus ions, and the cation exchange resin, you are going to get H plus ions there. No. Finally, H plus and OH minus combine to form water molecule. Means we are going to get deionized water. So ions will not be there. Means all ions are completely removed by cation exchange resin as well as anion exchange resin. So once again, synthetic resin method, it contains cation exchange resin, anion exchange resin. When you pass water through cation exchange resin, all cations of hot water are removed. In that place you are going to get H plus ions now. And when you pass hot water through anion exchange resin, all anions of hot water are removed. You are going to get OH minus ion from that. These two in turn will combine to form water molecule. Thereby we are going to get deionized water, means without any ions. Now next compound is hydrogen peroxide. We have preparation methods. Generally it can be prepared by acidic hydrolysis of peroxides. General method is you can prepare by acidic hydrolysis of peroxides will give us hydrogen peroxide. In that first one is hydrated barium peroxide with dilute sulfuric acid is going to give us H2O2. We can use peroxides and then hydrolysis can be done, but it should be acidic hydrolysis of is also peroxide. So let us take barium peroxide plus sulfuric acid is going to give us H2O2. Byproducts are barium sulfate and H2O we have. So acidic hydrolysis of barium peroxide gives rise to H2O2. The next one, electrolysis of 50% sulfuric acid with high current density is followed by hydrolysis, also gives rise to H2O2. Let us see the reactions here now. So compound used is 50% sulfuric acid and high current density is being used and followed by hydrolysis. So here in the first step here, that is H2SO4 ionizes to give us H plus HSO4 minus we have. Bisulfate anions, H plus ions are being formed. Now at cathode, so H plus ions move towards cathode. It requires 2 electrons, undergoes reduction, liberation of H2 gas takes place. When it comes to at anode here, at anode, the bisulfate anions move towards anode. So 2HSO4 minus move towards anode. Their oxidation takes place, means loss of electrons takes place. It forms here H2S2O8 plus 2 electrons. And this is called Marshall acid. So Marshall acid, also known as per-disulfuric acid. Marshall acid, also known as per-disulfuric acid. So 50% H2SO4 solution, high current density followed by electrolysis. First of all, ionization step. We have here H plus ions and bisulfate anions are there. H plus ions move towards cathode. Reduction takes place. Liberation of H2. Bisulfate ions move towards anode. Oxidation takes place. We are going to get H2S2O8 here, Marshall acid. Then, from the Marshall acid being formed here, upon hydrolysis, in stage 1 you are going to get H2SO5, which is also called Carros acid. This is called Carros acid. And this further hydrolysis is going to give us H2O2. So H2S2O8, which is called Marshall acid, on hydrolysis uses Carros acid, and Carros acid further hydrolysis, finally you are going to get H2O2 solution. In this way we can prepare from H2O2. Second one is auto-oxidation, means self-oxidation of 2-ethyl anthraquinol. 2-ethyl anthraquinol and auto-oxidation also gives rise to H2O2. So 2-ethyl anthraquinol, oxidation means the aerial oxidation itself. It gives rise to H2O2 plus 2-ethyl. It forms anthraquinone is being formed here now. Anthraquinol, that is OH group, forming anthraquinone. Nothing but it forms ketone there now. So undergoing oxidation now. So this is one of the methods to prepare H2O2 also. It is now H2O2 is extracted with water. It will be very, very dilute because water is there in that, and is subjected to distillation under reduced pressure. Subjected to distillation under reduced pressure to get 30% H2O2. Because when you are following normal distillation process, what happens is here H2O2 starts dissociating under normal conditions, will give us H2O and then oxygen gas. Therefore, it is subjected to distillation under reduced pressure only, not under normal conditions. With that process, you are going to get 30% H2O2 solution. Again, freezing further, you are going to get finally 100% H2O2 solution. So, the obtained H2O2 is going to be very much dilute because water is present in that. There are two steps to extract 10% H2O2. Step 1 is we are subjecting H2O2 solution to distillation, but under reduced conditions, not normal conditions, because under normal conditions we are going to get H2O and oxygen gas. That is step 1. You are going to get 30% H2O2 with that, and on freezing you are going to get 100% H2O2 solution. Then the 30% H2O2 solution is marketed as 100 volumes H2O2 solution. So 100 volumes means nothing but 30% solution we have, and then 10 volumes means it's only equal to 3%. So commercially available H2O2 solution is only 3% solution, which is also known as 10 volume solution we have now. Now here there are a few formulas to remember. Volume strength is given as normality into 5.6. This is volume strength we have. And we know that normality is equal to molarity into n factor. And n factor for H2O2 is 2. So into 2. So therefore finally normality is taken as normality is equal to volume strength by 5.6, and then molarity is equal to, it is volume strength by 11.2 we have. Volume strength by 11.2. These are the formulas to convert the volume strength to normality and molarity. And 10 volumes is a 3% solution we have. 10 volumes of H2O2 is equal to 3% H2O2 solution. So once you know the volumes, we can means 3% is equal to 10 volumes here. From volume strength, we can find out normality. From volume strength, we can find out even molarity also. Then comes structure of H2O2 solution. H2O2 is a non-planar structure. It is coming under open book shape. It is called open book structure. Open book structure here. And that is on the spine of the book. In the spine of the book, you are going to get 2 oxygen atoms are there in the spine of the book. You have 2 oxygen atoms here. And the 2 leaves contains 2 hydrogen atoms there. That is OH group. So 2 leaves contains hydrogen atoms in that. And the dihedral angle depends upon the state of that. This is called dihedral angle. This depends upon the state. Means in the solid phase, dihedral angle is 90 degrees. In gas phase, it is coming up to 111.5 degrees Celsius. So structure is non-planar. It is known as open book shape, and the spine of the book contains 2 oxygen atoms there, and the leaves contain hydrogen atoms, and dihedral angle is not same in both the phases. It is changing. In solid phase, the dihedral angle comes to 90.2, and in gaseous phase, it comes to 111.5. This is regarding the structure of H2O2. Then comes properties of H2O2. H2O2 acts as oxidizing as well as even reducing agent also. H2O2 acts as both oxidizing as well as reducing agent. When you take it, let us see now oxidizing properties. It oxidizes lead sulfide to lead sulfide. Suppose when you take H2O2 giving rise to the oxidizing property, use nascent oxygen, and with lead sulfide it takes the oxygen here and becomes now lead sulfate. When you balance this, it is a 4 here, so multiply this into also 4. By adding these two, you can cancel the oxygen here, means you are going to get here 4H2O2 plus PBS lead sulfide, giving rise to it is PbSO4 plus it is 4H2O. So oxidizing lead sulfide to lead sulfide. So it oxidizes black lead sulfide to white lead sulfate we have. This can be used to revive the color of old oil lead paintings also. So actually H2O2 can be acting as both oxidizing as well as reducing agents. It is oxidizing lead sulfide to lead sulfate. Then now oxidizing action in acidic medium, when you take acidic medium, is oxidizing ferrous salts to ferric salts in acidic medium. Ferrous to ferric salts. So Fe plus 2, you can take here ferrous sulfate, it becomes there. So when you take here say ferrous sulfate here, it is going to become here ferric sulfate. So Fe2, SO4, take and text. Should we remember that is oxidizing ferrous to ferric in acidic medium. Then in the basic medium oxidizing properties here, it oxidizes Mn plus 2. You can take MnCl2 type of salts, you can take there. So MnCl2 means MnCl2 gets oxidized to Mn plus 4 state. It forms MnO2, nothing but plus 4 state we have. In basic medium, it is oxidizing Mn plus 2 to Mn plus 4 state. So acidic medium and basic medium here. When it comes to reducing action of in say acidic medium first, it is reducing here MnO4 minus, means potassium permanganate changes into Mn plus 2. It is happening in the acidic medium then. Acidic medium, MnO4 minus becomes Mn plus 2. In the reducing actions, we can observe one point. Oxygen gas gets liberated in all these reactions here in reducing property. It also reduces hypochlorous acid to Cl minus ions. Means when you take here HOCl plus H2O2 here, we are going to get here HCl plus H3O plus it will be oxygen gas we have now. So means you can write here Cl minus here. Cl minus H3O plus and what or else HCl plus oxygen gas we can take. So it is reducing hypochlorous acid to Cl minus ions. Then in the basic medium, reduction action in the basic medium. The basic medium here, it is reducing halogens to corresponding halides we have now. Halogens corresponding to halides we have. Also reduces there now MnO4 minus to MnO2 in the basic medium. Also reduces MnO4 minus to MnO2 in the basic medium. These are coming under reducing properties in the basic medium we have. Uses of H2O2. It is used to bleach hair, used as a mild disinfectant. It is used as antiseptic, that is in the form of perhedrol. It is used in the manufacture of chemicals like sodium perborate and sodium percarbonate. It is used synthesis of hydroquinone, tartaric acid, and certain food products and pharmaceuticals like cephalosporin, etc. Then used for a bleaching agent for textile industries, means paper, pulp, leather, oils, etc. So used as a bleaching agent for textiles, paper, pulp, leather, oils and fats. It is used in the pollution control treatment of domestic industrial effluents. Used in the pollution control treatment of domestic and industrial effluents. Then comes heavy water, or called deuterium oxide. It is prepared by exhaustive electrolysis of ordinary water, gives rise to D2O, heavy water, prepared by exhaustive electrolysis of ordinary water. And it is used as a moderator in nuclear reactors. It is used to study reaction mechanisms in exchange reactions. It is used to prepare other deuterium compounds also. When it comes to properties of heavy water, they are similar to that of ordinary water only. So calcium carbide plus heavy water use C2D2. If you take here water, you are going to get there C2H2. So reactions are similar in nature. SO3 will form D2SO4 and aluminum carbide gives rise to CD4 plus ALO-D3 we have. So these reactions also are exactly same as that of water molecules only. Then dihydrogen as a fuel. It is used as a rocket fuel. It is a non-polluting fuel of a near future. Hydrogen economy is based upon the transportation and storage of energy of dihydrogen. It is used in the preparation of fuel for generation of electric power under the hydrogen fuel cell. So this is the